Suppose gamma is a patch. If it has length, we also say that gamma is rectifiable. Okay, of course, because for a patch C, we can define the length of C to be the length of any of its parametrization. Gamma is a patch which emerges C. Such a gamma is called the parametrization of our patch, our geometric patch C. Okay, but our previous lemma tells us that if another patch, parametric patch eta is equivalent to gamma, then they have the same length. That means you replace the parametrization of C gamma by another parametrization eta. They will have the same length. That is the length of this is not dependent on the chosen of the parametrization. Therefore, it makes sense to define the length of the geometric patch to be the length of any of its parametrization. Okay. So in this case, we also say C has length, or C is rectifiable. Okay. Now, another question we need to consider is that we know that two piecewise smooth, the union of two piecewise smooth patch is still a piecewise smooth patch once they have a common endpoint, so that you can join them together to get a new patch. Okay. But our next question is, if C1 and C2 are rectifiable, they have length, and they have a common endpoint, how about their union? Okay, naturally, intuitively, their union should be rectifiable also, and the length of the union would be the sum of their union. Okay, it will be the sum of the length of their union. So this is the next result we need to discuss. Let Ci be rectifiable. C1, C2 are rectifiable. And they have a parametrization, have a common endpoint, having common endpoint, so that they can join together. Okay, having a common endpoint, we don't need both endpoints to be coincide. Having a common endpoint, yes, a common endpoint. Therefore, we do not have S here. Then their union. Their union is also rectifiable, and the length of the union is the sum of their length. Okay. Now we'll prove this lemma. So it is not necessary to draw so complicated. So this is C1, and this is C2. C1 and C2 have range, or they are rectifiable. So for any epsilon positive, you can, for any epsilon positive, you have partition P1. Sorry, we need to choose a parametrization first. Let gamma 1 AB to Rn, gamma 2 BC to Rn be parametrization of our curve. Of C1 and C2 respectively. Of course, you might wonder why we can assume that gamma 2 is defined in the interval which left endpoint B. Okay, you might wonder this. In general, gamma 2 is defined in an interval alpha beta, but the alpha might not be B, right? But we can change the parametrization just like what we did in the previous example, previous argument. In this case, we define a new path gamma, so that the left endpoint of its domain of definition is B1. It's the endpoint of the domain of definition of gamma 1. That is A1, B1. Okay, gamma 1 ended at B1. Gamma 2 start at A2, but A2 is not necessarily B1. But we can replace gamma 2 by a new patch gamma, a new parametric patch gamma, whose domain of definition start at B1. And this new gamma, the image of this new gamma coincide with the original gamma 2. So this new gamma is also a parametrization of C2. Okay, so we can use this trick again to assume that our gamma 2 is defined in the interval BC. In particular, the starting point is B. Just equal the endpoint of the domain of definition of gamma 1. Gamma 1 is defined on AB. Now we assume gamma 2 defined on BC. This will not lose of generality. Okay, so gamma 1, C1 and C2 are rectifiable. So that is gamma 1 and gamma 2 are rectifiable parametric patch. Okay, so for any epsilon positive, we can obtain the partition of AB and BC. So we have some corresponding to the curve. There are some points on the curve. So some partition of the interval will give us a partition of the curve. So for any epsilon positive, we have partition. We have delta positive, such that if partition P1 of AB and P2 of BC verifies gap less than delta, then the range of the inscribed polygonal will very close to the range of C1 and C2. This is the range of the curve gamma I, which with respect to the partition Pi will very close to the range of Ci. That is the difference which absolute value less than epsilon. Okay, and we might also assume by the uniformly continuity of gamma 1 and gamma 2, we might also assume that gamma 1b minus gamma 1t plus gamma 2s minus gamma 2b less than epsilon, as long as s and t belongs to the neighborhood of b minus delta, b plus delta. Okay, this is the consequence of the uniformly continuity of gamma 1 and gamma 2. Because if st belongs to the interval b minus delta, b plus delta, then the distance from of t to b and s to b will less than delta. Therefore, the distance from gamma 1b to gamma 1t will be very small, and the distance from gamma 2s to gamma 2b will also be very small. We can require their sum to be smaller than epsilon. Okay, so we want to prove that the union is rectangular. So for such gamma 1 and gamma 2, the union has a parametrization. Gamma 1, gamma 2, with the union of these two curves we denoted by gamma 1, gamma 2, which is the curve gamma AC. We recall the definition where we have used before. Okay, to prove the piecewise smoothness, we have already introduced this curve resulting from gamma 1 and gamma 2. We record it here again. That is gamma t is gamma 1 t for t in AB, gamma 2 t for t in BC. Okay, so this is a parametric curve, piecewise smooth. And suppose P is a partition of AC. And of course, P has some point Ti, I from 0 to m. So this is the interval A, B, C. Our P is the partition. Okay, so we might assume that B, the point B here, we might assume B in some subinterval. We might assume that B is in the subinterval T j minus 1 Tj. T might be a point Ti. So the subinterval containing B, I use a half open interval. I will assume B is less than T I j minus 1, but it might possibly equal to Tj. Okay, so I use this interval. There is a unique interval of this form, left open and right closed interval containing B. There must be some j between 1 and m for some j in 1 and m. Such that B in such interval. So using this partition, we want to consider the length of the curve, the length of the inscribable polygonal of gamma, which respects this partition P. We want to consider this quantity.